Hey guys, welcome. This will be a recitation or whatever if you want to. I know at Tech they don't usually do recitations, but I'm going to do it. So like I said, I want you to get used to it. On Tuesdays, we'll have the lectures, and on Thursdays, I will send you some problems in advance after Tuesday's lecture, and then you will have some time to solve them. I don't know, like a day or something, but you can also solve them in those 30 minutes before, well, during the class, in those 30 minutes. And then in the next 50 minutes, we'll discuss them. Okay, I think I assigned a couple of problems. Let me.
Dude, can you like log out of the other Zoom one?
Just a second.
Or like turn your camera off?
Yes. Okay, turn the cameras on. Okay. All right. Let's see. Problem one. Did you try solving this problem? I know some of you already did, but. So problem one said the following: find the minimum minimum value of the expression. Let's say it's x plus 1 over x to the power 6th minus x to the 6th plus 1 over x to the 6th minus 2. And this will be over x plus right? I think that was the problem, correct? Right, let me just double check on my website. But I think that was the correct statement. Worksheet one, okay. Yes, that was the statement, right? Okay, some of you already did this problem, but anyway, it's quite easy. This was a Putnam B1, I think, in 1998. Right? And well, the main idea here is quite simple. You are tempted to, at first, to try the following. Maybe you should just, you can do the following substitution, something like x plus 1 over x equals a. But if you do this, well, if you do this, actually I tried to do this and the computations are quite heavy, and I think I've done computations wrong a couple of times, and then okay, I decided to give up, because if you look at this, if you denote x plus 1 over x equals a, let's say, then you have to raise to the power, maybe you can write that 6, everything to the power, everything squared and then cubed, but then the computations are not nice. So it's better for you to do the following. Maybe maybe you should put a to be x plus 1 over x to everything cubed, and you will see why, because I will square this, and b to be x cubed plus 1 over x cubed. And then let's see, what do we have? If you look at this guy, x plus 1 over x to the power 6, this will be nothing else than just what? Just a squared, right? And now, if you look at this guy, x to the 6 plus 1 over x to the 6 minus 2, well, guess what? If you okay, if you square this guy here, b, right? Let's square, let's see. Okay, let's write it like this. It's x cubed plus 1 over x cubed, everything squared, right? And this will be x to the 6th plus x to the 6th minus, plus plus 2, right? So let me, okay, maybe here plus 2, I should write it. Because this expression here, I can write it as x plus 1 over x, everything to the power of 6 minus x to the 6th plus 1 over x to the 6th plus 2, right? Everything over x plus 1 over x, everything cubed, plus x cubed plus 1 over x cubed. In any case, the point is that this expression, let's call this E, will become the following. Then E will become what? Can you tell me based on these notations? So the first one will be a squared minus b squared, and then here you have a plus b, right? But you know how to, you know that this is a minus b times a plus b over a plus b. These two will cancel and is nothing else than just a minus b, which is, in our case, x plus 1 over x cubed minus x cubed plus 1 over x cubed, right? And now, this will be equal if you expand everything here. It will be, this guy is x cubed plus 1 over x cubed plus 3 x times x plus 1 over x, so minus these guys will go away. So this will be 3 times x plus 1 over x. So you can actually simplify this. This is just a simple algebra. Okay, and now we want to find the minimum of this, which is quite easy by AMGM. You don't have to use the derivative. So by the arithmetic geometric mean inequality, we have what? We have that x plus 1 over x is greater or equal than 2 square root of x times 1 over x, which is 2. So this guy here will be greater or equal than 6. So the minimum value, so minimum value of E when x is real, yeah, for x positive, is 6. Well, can you tell me when when is this value attained? And is attained. When do we have equality in the arithmetic geometric mean? When? We said that equality we have in the arithmetic geometric mean, let me remind you, that alpha plus beta is greater or equal than 2 square root of alpha beta, right? In general, with equality, if and only if alpha equals beta, right? This is when we have equality. So this will have equality when x is 1 over x, and if you solve this equation, because x is positive, it will give you x equals 1. So this is when we have equality. So the minimum is 6, and it is attained when x equals 1, and that's the problem. Wasn't that hard, wasn't it? Was it? Anyway. Let's see. The second problem. So I have ABC positive, and I need to show the following inequalities. All right, the first one was, okay, I'm gonna just, for the sake of gaining some time, I'm gonna write it like this. So the product of A plus B is greater or equal than 8 ABC. So that was the first inequality. Then the second one was the product of A plus B is greater or equal than 8 over 9 sum of AB. Right? And the third one is this. We have here the sum of cubes. I think I showed you in the lecture something with the sum of the squares, a particular case of Cauchy-Schwarz. And then the last one is this guy. All right. So let's see. What did you try here? For the first one, I think I just mentioned earlier, if you look here, the only thing you need to do is just to apply the AMGM. You see, it's written in red there, and for the first one, right? So let's see. The first one, by the AMGM, what do we have? So we have that A plus B is greater or equal than 2 root AB. B plus C is greater or equal than 2 root BC. And the last one is C plus A is greater or equal than 2 root CA. Well, multiplying all these together, what do we have? Guess what? We have exactly what we want. Let's do it. A plus B times B plus C times C plus A is greater or equal than 2 root AB, 2 root BC, and 2 root CA. And when you multiply this, it will give you 8BC. So it was just a direct application of the AMGM inequality. Okay, so that was the first one. The second one, maybe I should put here like this. Ouch. Okay, so the second one, well, it's, if you look at it, it's a little bit, well, let me point out a remark here. If you apply the AMGM, so it's a sharper inequality than the first one, right? Because if you apply the AMGM on the right-hand side, so by the AMGM, inequality, we have that, you know, that the sum of A is greater or equal than 3 root 3 ABC, and the sum of AB is greater or equal than 3 root 3 A squared, B squared, C squared. And when you multiply, and this gives us that the sum of A times the sum of AB is greater or equal than, when you multiply this together, it will give you 9ABC. So as you can see, we obtained the first inequality if we assume the second one. So now we cannot use, you see, I have the same expression, the product of A plus B there. And now I have to see something about this.
Sorry, what are we working on?
Problem 2, we already done problem 1.
Okay, part 1 of problem 2?
Part 2 of problem the product of A plus B greater or equal than 8/9.
Oh, I solved that one.
Oh, you solved this one?
Yeah.
Oh, great. Maybe, okay.
I just finished part 3 of problem 2.
Uh-huh, okay.
I managed to do all of it. That's why I was late, sorry. I got caught
nice.
up.
Nice. That's good. Right now, I was just pointing out the fact that you cannot, you see, we have the same expression for part 1 and part 2 on the left-hand side, and maybe you're tempted to say, look, maybe I could use part 1 to solve part 2, but that's not the case because it's the other way around. So we have something like this. So the inequality is stronger. So we have, let me point this out, that the product of A plus B is greater or equal than 8/9, which this one is we want to solve, times the sum of AB, and this is greater or equal than 9ABC. Sorry, 8ABC, right? Because this is greater or equal than 9. This guy we just said that is greater or equal than 9ABC. So how to solve this? Well, Gabe, okay, I'm gonna pronounce it in Romanian. Gabriel, since you are a Romanian. Gabriel, how did you solve this?
I think it was by, yeah, it was by arithmetic mean and geometric mean, just like the first one.
But directly like this? Because that's the point, it doesn't work directly.
Let me see.
Because this is how we solved the first part, right? It was a directly arithmetic and geometric mean.
Yeah.
But
yeah.
this part has something something extra to it. You need to do something.
The 8/9.
Yes. The first one, yes, indeed, you solve it by an application, as you can see. You can use the arithmetic geometric mean inequality. But now here, I gave you some identity in the lecture.
Is it the shear inequality?
No,
not the shear, the one with the 9.
So I gave you, remember this identity? Let me recall. And I told you to prove it. This identity, the product of A plus B, this can be expressed in terms of the symmetric sum. So this is very nice, minus ABC. So once I use this, because here I don't use any inequality, so the point is to use this, not to use inequalities, try to use as many identities as possible so that you can simplify things. Because when you use inequality, you might use an inequality that will be too weak for your purpose. So that's why you need to be careful with the inequalities.
Yeah, I think I made a mistake on it.
Okay. Because it doesn't follow directly. So, well, modulo this identity, yes. So the inequality reduces to, and you will see what it will reduce to. Reduces to what? Well, to sum of A times sum of AB minus ABC is greater or equal than 8/9 sum of A, sum of AB. Well, now if you, and this will be equivalent with what? Which is equivalent to what? To sum of A times sum of AB right?
Right.
1 minus, so it will be 1 over 9. You take this, it will be greater or equal than 9 ABC. Well, did we just prove this earlier? Look here. We just proved it. Look, it's right here. Since we wanted to see which one is sharper, but actually when we would try to see this, modulo this identity, we actually reduce the inequality to this. And this was proven earlier. So that was the second. Anyway, the third one, I will leave it to you because there are a bunch of computations. I did this. So I'll leave it to you, the third one. But the thing is, you can use, let me just tell you what to use. You can use some identities here because you have cubes and everything. And one identity was this one that I gave you in the lecture, is the sum of a cubed minus the sum of a. Cubed is nothing else than just the 3 times the product of a plus b. And then at some point, you will use this the above identity as well, and then you'll figure out that this is nothing else. At the end of the day, it will be just an AMGM inequality. But anyway, the details are a bit sketchy, so I'll leave them to you. Okay, and now for the last one.
The way I solved it, I expanded it. Does that work, or do you think I did something wrong?
Yeah, I think it works. Yeah, because you have 9 to the sum of a cubed, and you expand that, you'll have, you can. But I was trying to avoid the computation because when you expand that cube, right, you have to expand it to the square, and then you multiply by a plus b plus c, right? This is how you did it.
Yeah, I got 27 terms from it.
Oh my goodness! You see, I'm trying to avoid that. If I write here 27 terms, I will not have time to do the other problems. But at the end of the day, you got something like obvious, like AMGM or something like this, right?
Right. I got so I got 3 times a third plus b third plus c third plus a plus b plus c times a squared plus b squared plus c squared minus ab minus bc minus ca is all more than or equal to 0. And then I just had to prove each individual part was more than 0, or more than or equal to 0.
I don't think, I'm not sure if it, well, after you've done all the computations, you end up with that expression, right?
Yes.
I don't think you can prove that each one of them is greater or equal than 0.
Well, it's because a, b, and c are all individually greater than 0.
Yeah, but you have a minus there. You have minus something, so you don't know how to.
Right, but I have an inequality that says a squared plus b squared plus c squared is more than or equal to ab plus bc plus ca, don't I?
Ah, okay. And yeah, I think that's more than enough. Yeah, if you use that, okay, that's great. Yeah, yeah, probably it will end up proving just that inequality. But anyway, to avoid heavy computations, you try to make your life as easy as possible, try to use these identities. Anyway, the last one, we have to prove that the 3 times the sum of a cubed is greater or equal than the sum of a times the sum of a squared. Well, here, if you expand this, so this guy here, right, it will give you the sum of a cubed, right, plus, and at some point when you multiply here, let's say ab squared, ac squared, or the other way around, it will give you the sum of ab, let's say, times a plus b, right? This is what you're gonna get. And then this inequality will reduce to, this reduces to 2 sum of a cubed greater or equal than sum of ab times a plus b. And now you can, well, it's just computations. Now what you can do is I give you this inequality in the lecture. Okay, let me, using the inequalities, we're going to group them 2 by 2. And I'm going to look at this guy here. So using the inequality, let's say a cubed plus b cubed. Remember I gave you this is greater or equal than ab times a plus b, right? This was given in the lecture. And the way we prove this, well, I didn't say, but it's this is a plus b times a squared minus ab plus b squared. And everything will reduce to just a squared. This is for all a, b greater than 0, but anyway, it holds even for the sum to be positive. And this will reduce to what? Will reduce to, this is equivalent with a squared plus b squared greater or equal than 2ab, which again follows by AMGM, or you can just take the 2ab on the left-hand side and it's just a minus b, everything squared, which is non-negative. Okay. And now we want to use this. Similarly, what do we have? B cubed plus C cubed is greater or equal than BC times B plus C, right? And C cubed plus A cubed is greater or equal than CA times C plus A. Guess what? When you add them up, so when we add them up, we get exactly this. Right? I think it's obvious. Okay, so that was the trick of the problem. Anyway, that's good to keep in mind. Now, problem 3, we've done this in class. What about problem 4? Did you do problem 4? So the first part was when basically says that this is a very nice application. Well, it's a special case of Cauchy-Schwarz. And alpha 1, alpha 2, alpha n is positive. These are positive numbers. Show that, okay, I'm going to write it like this. The sum of xi squared over alpha I is greater or equal than the sum of xi squared, everything over the sum of alpha I. Okay. Well, like I said, this is just a special case of Cauchy-Schwarz. And I'll say immediately why. You can prove it by induction if you want. Well, yeah, I'll leave it to you as an exercise to prove it by induction. For example, for n equals 1, there is nothing to see. For n equals 2, you will see that there's just something, a real number squared, which is not negative. And then you keep going. It's a straightforward induction. What? Wait, something happened here. All right, sorry about that. So like I said, it's a straightforward induction, but now let's see how this is a special case of Cauchy-Schwarz. Well, let's rewrite this. Rewrite the inequality. as the sum of alpha I we can rewrite it in this way. Can you see the Cauchy-Schwarz here? Let me remind you what Cauchy-Schwarz said. So Cauchy-Schwarz inequality says the following, that if I have these numbers A1, A2, AN, and B1, B2, BN, these are real numbers, then the sum of AK squared times the sum of BK squared is greater or equal than this guy here.
Shouldn't, since you squared the I inside of the parenthesis on the left, the xi, shouldn't it be xi squared over alpha I times alpha I? So shouldn't it be xi squared in the within the on the right side?
Okay, here. No. You mean here in the first inequality, the way I rewrote it? No, look.
No. So in the one where under where it says solution.
Yeah.
So AK is square root of alpha I. And BK.
So exactly. So let's identify. So AK is what? The square root of alpha I.
BK is xi over the square root of alpha I.
Okay. That's very unfortunate notation. Okay, let me just stick to the note. I changed it. KAI. Okay, give me 1 second. So here it's I. I
see it.
Okay, I. And here it's I, not K. Again. AI squared, BI squared, AI, BI. Okay. And now, just like Gabriel says, you take alpha AI to be what? The square root of alpha I, right?
Yep.
So take
BI is xi over square root of alpha I.
Exactly, xi over square root of alpha I. And apply Cauchy-Schwarz. Keep in mind this special case. You might use it, and for examples and with the application, right? Is it clear for everybody? How is this Cauchy-Schwarz? Right? Because you have this, right? You can rewrite this in the following way. You can have the sum, the square root of alpha I squared times the sum of xi over square root of alpha I squared, which will be greater or equal than this squared, which is nothing else than just the sum of xi squared. That's it. Right? Okay. What about the application? Did you guys do the application? Because I think this is new in the homework. Jack, did you do it?
No, I saw that it was a new application, and that's what I was working on.
That was not the, well, I want to say, let's see the application. So what was the main idea here? So this application said the following. So let n be a positive integer And also let these numbers A1 AN and B1 BN, these are real numbers such that AI plus BI, so I want the denominator of each fraction to be positive for all I want from 1 to n. Okay. And we have to show that that this sum AI BI minus BI squared over AI plus BI is less equal than this sum here, AI plus BI, and on the numerator we have this sum. Minus the sum of BI squared. Well, this was an IMC problem, surprisingly. The IMC, it's called the International Mathematics Competition. It's a worldwide Putnam. So that, because these, in Eastern Europe, we cannot participate in the Putnam, so it's North American, but we can participate in the IMC. It's very similar to the Putnam.
We call it the Olympics.
No. This is for university students. It's International Mathematics Competition for university students. That's the IMO, International Mathematical Olympiad for high school students. This is for university students. So we have a competition of our own, and also there are some others, but this is one of them. Anyway, it's imagine that it's a worldwide Putnam. You can participate. If American students can participate, or any student from North America can participate in IMC. Anyway, there are some costs because usually it's held in Bulgaria and so on. And then this is one of the problems. Well, if you look at it, I put it as an application. It doesn't look like an application at first when you look at it, right? It seems that, well, but if we look at it, let's look at it closely. Maybe we can do something. Well, how about a magic trick? I want to say it's magic, but it is a trick. Maybe I can rewrite this expression. As you can, if you look at both the expressions, you see you have the sum of this guy here inside. Let me point out. Look at this guy inside here. It's very similar to this guy here. The only difference is that these are, let's say, sums of each one of them, right? But here the sum is this. Here the terms are inside, but they look very similar. It's AI BI minus BI squared, and on the right hand side you have the sum of AI, the sum of BI minus BI, the sum of BI squared. So it's more like very similar expression. You see, on the right hand side you take the sum of each one of them. On the left hand side you take the sum of all of them. So maybe I should do a trick that will to do a trick to the expression on the left-hand side that will be useful to the expression on the right-hand side as well. So what should we do?
We could set. Sorry.
Say it.
We could set the sum to like. So the sum over the denominator doesn't really matter. Or no, it does. That was stupid. Sorry. Continue.
No problem. Oh, anyway, so let's see. Because let me look at this guy. In fact, let me write it with red. AI BI minus BI squared, everything over AI plus BI. And now what I'm going to do is the following. because I'm trying to get rid of the denominator AI plus BI. So maybe I should do a trick in that sense. So maybe I should do something here. Maybe just force a factor. Let me take a BI here. It's AI plus BI minus 2BI squared, right? So I add and subtract an BI squared. That's what I do. Because now my life becomes easy, right? This is nothing else than just the sum of BI, AI plus BI over AI plus BI minus 2 times the sum of BI squared over AI plus BI, right? And now you can look here. This is nothing else than just the sum of BI minus 2, the sum of BI squared over AI plus BI, right? Okay, so I managed to write the left-hand side. Now let's do the right-hand side. Similarly, the only thing here, the only difference is that I'm going to force a factor the sum of BI. So similarly, we have, so let's see, what do we have? Okay, let's write it. The sum of AI times the sum of BI minus the sum of BI squared, right? Over the sum of AI plus the sum of BI, let's say. Because now I want to do the same thing. You see, it's the same expression here. The only difference is that I have the sum here from 1 to n. You can understand that this is from 1 to n, but I didn't want to write it, so I don't lose any time. So I want to do the same thing. So what should I do? So maybe I should force the sum of BI as a factor this time, not just BI. Times, here I will have the sum of AI plus the sum of BI. Okay, let me write it down. So this will be equal to the sum of BI times the sum of AI plus the sum of BI so I have minus 2 times the sum of BI squared. This is the same trick. And here I have everything over the sum of AI plus the sum of BI. Right? Well, guess what? I'm going to do the same thing. So is it clear for everybody what I did?
Yeah.
So I'm just multiplying and subtracting the sum of BI squared. That's what I'm doing. And now I can do the same thing. So this is the first one will be the sum of BI, because this guy will cancel, minus 2 times the sum of BI squared over the sum of AI plus the sum of BI. That's what we get. Right? And now let's put everything together. So this guy is the right-hand side, and this guy here is the left-hand side. So we have to, you see I have a sum of, the inequality reduces to reduces to what? So let's see, the left-hand side is the sum of bi minus 2 times the sum of bi squared over ai plus bi, which is less or equal than the sum of bi, the right-hand side, as you can see it above, minus 2, and let me write it in this way, the sum of bi squared, so everything squared over the sum of, okay, let's write ai plus bi is the same thing, right? This guy will just go away. I'm going to reverse this, so this is equivalent to what? To the sum from n equals 1 to n of bi squared over ai plus bi is greater or equal than what? Than the sum, oh,
Isn't it less than equal?
no, because look, I have a,
multiplied by -2, right?
and I cancel -2, but I take this guy on the, so yeah, multiply by -1. We'll have this over, now do you recognize this guy at this point? When you look at it? Does it ring a bell? Is it an application of the lemma? Or of the previous problem? Look at the previous problem. You see it? Look at it here. Is the sum of xi squared over alpha I. So who is xi in our case?
Xi is square root of bi.
No, it's just bi. Look.
Oh yeah, just bi. Yeah.
So take xi to be bi and alpha I to be ai plus bi, and apply the previous inequality, the previous problem, let's say. Let's call this the special case of Cauchy-Schwarz. And that's it. And we're done. C'est fini. That was the problem. Okay. Jack, what do you think? Was it tricky? Was this problem tricky?
Yeah, a little bit.
A little bit, right? Anyway, it was considered to be medium hard problem. Well, medium for the competition. But you can expect something like this in the Putnam. In fact, let me veer towards problem 5. Let me quickly say, because well, I'm running out of time, but anyway, you can log out any time you want. So problem 5 said the following: to find all positive integers k1, k2, kn, right? Such that the sum of I of ki is 5n minus 4. This is 5 here. And the sum of the inverses is 1. Well, I said something in my class, right? In the lecture, in the previous lecture, we have this arithmetic, well, we have these inequalities. Let's call this alpha I over n, so the arithmetic mean is greater or equal than the geometric mean. and greater or equal than the harmonic mean. So this is the arithmetic mean. So we said it for two numbers, but this holds true for, this is the geometric mean. This is the geometric mean. And this guy is the harmonic mean. So let's apply, and we call this AM, GM, and HM, right? And now, as you can see in our problem, if you look at it, I have the sum of the positive integers, the sum of the inverses. So it's quite clear what to do. So by the arithmetic, by the AM-HM inequality, we have, what do we have? So we have, if you look at it, the sum of Ki times the sum of 1 over Ki is greater or equal than n squared, right? This is what we have. If you just use the AM HM inequality. But this guy is 1. This guy is 5n minus 4. So we have that 5n minus 4 greater or equal than n squared, which doesn't happen for all n. And you will see that from here it follows that n is less or equal than 4. And now you have to find those integers. And now you have to check each case, n equals 1, n equals 2, n equals 3, n equals 4. So without loss of generality, you can assume that K1 is less than K2 less than Kn, right? And and then let's see, for n equals 1, okay, I'm just gonna tell you directly. For n equals 1, you can take K1 to be 1, okay? And we're gonna exclude this case for these numbers for n equals 2 and so on. Here, for n equals 2, once you, it's easy to see that we have these K1, K2 are, the only options you have is 2, 4, and 3, 3. And neither of them work. Then for n equals 3, what do we have? Well, we have a bunch of triplets here, K1, K2, K3. This will be, let's see, oh my, we have a bunch of them. So we'll have, let's say 2, 2, 7. What else do we have? 2, 3, 6. 2, 4, 5. 3, 3, 5. Yes. And 3, 4, 4. Anyway, I don't think I missed any case. And the only thing that works here is this guy.
Doesn't 1, 5 work as a case for n equals 2?
Which one?
Like it doesn't work, but isn't that also a case? 1, 5 for K1, K2?
1, 5.
Because they have to add up to 6, right?
So for n equals 2.
Right.
Wait. So for n equals 2, yes, they add up to 6. Yeah, but the sum of the inverses, is it 1?
No, I'm not saying it's 1, but that's a case too, right?
Oh, okay, yeah, actually you're right. Yeah. 1, 5, yeah, correct. Yeah, I forgot about it. Yeah, 1, 5. 1, 5, 5, 1, and so on, but neither of them work. So the only thing you look for all of them and you'll see that only a few of them work. And for n equals 4, the situation is simpler because we have equality case in the, HM inequality. So we can exclude many of them. So when do we have equality? When this happens if and only if all of them K1, K2 equals K4 equals 1, right? And you'll see that these are the only cases that work. Anyway, that was the problem. And I want to do another problem, just give me 2 more. Anyway, you can log out. Problem 7, or at least just tell you the idea. So problem 7 said the following. Let me find it here. So suppose that these guys, A1, A2, AN, are real numbers. And n is greater than 1. And such that we have this inequality. It's very strange inequality, I would say. Well, strange. It's not the typical inequality. Okay. Prove that A is less than 2AIAJ, right? Or I less than J less than N. So this was a Putnam B5 in 1977. All right, you'll be tempted to use a Cauchy-Schwarz directly because we know that the sum of the A squares is greater or equal than 1 over n, the sum of AI, but it won't give you anything. That's the trick. So a direct application of Cauchy-Schwarz doesn't really work. Well, but there is something, maybe a trick using Cauchy-Schwarz would work. And let me just give you the main idea, since I don't have much time left, and I'll leave it to you to complete the details. What I'm going to do is the following, and bear with me. So we apply Cauchy-Schwarz inequality in the following way. And what I'm going to do is the following. Bear with me. Anyway, it doesn't really matter. I can prove there that A is less than A2 times A1, A2. It doesn't really matter. So I will do the following trick now. In fact, let me write it. Okay, here we go. Look. So I look at this guy here, A1 plus A2, but you can put any AIAJ. You can pick any of them, but I can pick these. I'll group them together, and then I'll put A3 plus A4 plus so on plus AN. And this guy is everything squared. And look here, I have, how many terms do I have here? If I group them, no.
Oh, n minus 1. So it's an average.
Because this guy A1 plus A2, I group them together into one term. So this will be less or equal than what? Then let's write it 1 squared plus 1 squared plus 1 squared. Here I have n minus 1 times, right? Minus 1 terms times what? Times A1 plus A2 squared plus A3 squared plus AN squared. So that's the Cauchy-Schwarz. Anyway, you'll see some details here because when you expand this guy, that's the trick here. You'll get this term A1 squared plus A2 squared plus 2A1, A2, which is exactly what you wanted to derive. You want to write in terms of this guy. Anyway.
Could we, I was wondering, because I was looking at the equation, for the A is less than or equal to 2 AIAJ,
Yes.
right? And they specifically mentioned that AI and AJ are different from each other and that they're in between those. wouldn't it make more sense to rewrite it as AIAJ are the first two terms, since that is the strongest?
Like I said, it doesn't really matter. Yeah, you can write, it doesn't really matter. If you prove it for the first two terms, it's the same for the other. So without loss of generality, you can prove it. It doesn't really matter. So as you can see there, I can put any AIAJ, but I have to be careful that those AIAJ, I have to, that's why I didn't want to bother with this. I just put A1 and A2 and that's it. So at this point, it's just computation. So just, and good luck with the computations. But that was the main idea. So you see, the main idea was to look at, to get these guys to A1, A2 from somewhere. And that was the trick. Anyway, it is tricky, I admit, because if you apply Cauchy-Schwarz directly, it doesn't give you anything. Okay, guys, I'm going to stop here. Thank you very much. I already went way over time, but I hope it's all worth it. And I'll see you on Tuesday. We'll continue. We'll continue with elementary algebra, but we'll do something. Maybe I should do a little bit about complex numbers, and then we'll talk about sequences, induction, and then polynomials. Okay.
Thank you. Yeah, we're good.